Welcome to the Shape of Space Matrix Calculus. This is the first lesson in a series of 5 lessons on matrix calculus. It follows 2 earlier playlists that I've put together, one on linear algebra and another one on matrices. I assume that you know that information, and I'm going to build on that as I proceed here. In this overview lecture, I'm going to talk about the topics that will be covered in the subsequent lectures in this playlist. And then I'm going to just give you some examples of the type of problems we're going to look at, but not any solutions, just the types of problems that will be discussed later in the additional 4 lessons. These are the topics I'm going to cover in the 4 lessons that follow this lesson. Some of them are combined into one lesson, so that's why I have more bullet items here than I have lessons. So we'll start with derivatives of scalar and vector functions, the gradient and Jacobian. This is something from usually the 3rd course in calculus, multivariable calculus that people take. And I assume you pretty much know that, so what I'll have here is more of just a quick review. What I really want to get at are the dual numbers, and then derivatives as linear operators, which make use of the dual numbers. And then talking about some subtopics here, directional derivatives and the Fouché derivative. Then I'll get into first derivatives using this concept of linear operators for scalar valued functions, vector valued functions, and matrix valued functions. And then I'll talk a little bit about the Hessian and second derivatives. And then I have a slide towards the end of the last lesson on further study, where I give you some links to other videos that you might want to pursue to get more information. What I want to do here is go through the various levels of complexity in terms of derivatives. I assume the listener has already taken a calculus class and is familiar with derivatives. And so this is more in terms of a review. I will get into things that are not covered in typical calculus, but that's in some of the latter lessons. So we start here with the simplest case. We have a scalar input and a scalar output. F of x equals x to the n would be an example. And then we know the derivative is n times x to the n minus 1, so that's also a scalar input and a scalar output. For the examples in this lesson and in the following lessons, the elements of the vectors are assumed to be, and matrices are assumed to be real or complex. And the vectors are assumed to be column vectors. If we need a row vector, I'll either write it out as a row vector, or I'll take the transpose of a column vector. Then moving up from this simple case of scalar input, scalar output, we can have functions with vector inputs and scalar outputs, or functions with scalar inputs and vector outputs. And I have an example of each. So here we have f of x, y, z, so there's a vector input, but then the output is a scalar. It's just various products and sums of the inputs. And then another example would be scalar input, vector output, and that's, you have a single input, but then you expand that out to 3-dimensional vector in terms of its output. Then moving up one level of complexity from that, you could have a vector input and a vector output. Here we're going from 3 dimensions to 2 dimensions. I have several more examples in the next couple of slides, getting progressively more complicated. Let's look at some additional cases with vector inputs. So x here is a column vector in all these examples. And I'm just giving you the statement of the problem here. Later on in the subsequent lessons, I'll talk about solutions to at least some of these. So the first one is we have a vector input x, and then x transpose. I just did this because normally the norm of a vector is it takes in a row vector. So this is an example. You have an input that's a vector, and then the output is, since it's the length of x, it's just a single scalar. And here you have another example, f of x equals x transpose times x. That's the inner product. And again, that would be a scalar. Then we have another one here. It's a little bit more advanced. It involves a matrix A, but still, when you multiply these together, because of the dimensions involved, you have a row vector here. X transposes the row vector, so that's 1 by n times an n by n. That's 1 by n, then times x, which is n by 1, and so you get a 1 by 1 output, and that's a scalar. Then you can have a vector input and a vector output. So f of x equals ax, basically a system of equations here, so this is a common one. Then here you have f of x equals x divided by x, the norm of x transpose. This is just the length, so you're basically normalizing your vector x, so you still have a vector. And then here we have a vector input and a matrix output. This is the outer product, which I discussed in my linear algebra series. And when you take a column vector times a row vector, you're going to get a matrix, an n by n matrix in this case. On this slide, I have functions that have matrix inputs. And we'll look at the derivatives of these later on. These are not typically covered in a basic calculus course. So the first set of examples, the matrix input was a scalar output. So here the capital X is a matrix, and the other things are vectors. So you have A transpose X times A. Or A is a constant n by 1 column vector. X is n by n. So when you multiply these together, you get a scalar. Then the next one is the trace of x. If you recall, the trace of x is just the sum along the main diagonal. So that's a scalar. Then we also know the determinant of a matrix is a scalar. So that's yet another example where you have a matrix input, but the output is a scalar. Then we move up one level. You can have the matrix input and a vector output. So we have a matrix times a constant column vector. So that would give us a vector. And then if you recall from the series I did on matrices, the vec, where you vectorize a matrix by stacking its columns one above another in a long vertical vector, column vector. This would be a vector, so you'd have matrix input, vector output. Then the hardest case is matrix input, matrix output. Again, X is a matrix here, so X to the n is also a matrix. Then you can have f of x in the output e, the exponential function raised to the e raised to the x power, and that's normally defined in terms of a power series. So we'll look at some of these. In fact, we'll look at most of these in the subsequent lessons. And we'll use different techniques here beyond just what you've seen in multivariate calculus, where we talk about gradients and Jacobians. That doesn't really work easily here for these cases. So we'll use something else, which I'll talk about. Okay, so this is the overview, and as I said, there's 4 more lessons in this series.